All right, we're going to take a look at some more chi-square problems. Once again, I put the actual chi-square equation here. Remember, you don't square the answer, it's just the name of the test. So, chi-square value will be the sum of all of the categories with the observed minus the expected squared divided by expected. Again, at the very end, don't forget, you have to sum up the results of all the categories to get your chi-square. All right, so we're going to do this with a genetics problem. So we're going to have to relearn how to do Punnett squares, or at least remember how to do Punnett squares. So this is a pea plant question. In peas, green seeds are dominant over yellow. All right, well, let's assign a big G for green and for yellow, the recessive little g. A cross between two plants that are both heterozygous for seed color, the following was observed. So here's our observed data. All right, well, that's easy enough. They give us our data already. Now we need to figure out expected data. Well, for genetics experiments, we can figure out our expected values using our Mendelian rules. Basically, just using Punnett squares. All right, well, if I did a Punnett square for this problem, to get my expected results, I would need to cross two heterozygous plants like this. And then, as you already know, we've got 75% are going to be green and 25% yellow. All right, let's make a chart to make this easier. Got my observed and my expected, my two different categories, green and yellow. Remember, my degrees of freedom is always the number of categories minus 1, which makes our degrees of freedom 1. Over here, I'm going to also need totals, since I'm dealing with percents over here. All right, so 4,400 is what I observed to be green, and 1,624 what I observe to be yellow. All right, so what's that total then? 6,024. Well, that should be the same case for both. All right, now I find expected. 75% of 6,024 should be green. So 0.75 times 6,024 is 4,518. All right, well, 25% then should be yellow. 0.25 times 6,024 gives me 1,506. All right, now I'm ready to go. I'm ready to plug my numbers into the formula. In our last problems, you had a chart to do this, but you don't really always need the chart. You can make one if you like, but sometimes it's just easier to write it out. All right, so observed, 4,400 minus expected. Don't forget to square that and then divide by the expected value. All right, that'll be for green. Remember the sum of our categories, so make sure you put a plus in between there. 1624 minus 1506. Square that and divided by expected. All right, then you can do the math on that. So for this, I will get 3.08. For this one, I'll get 9.25. and that will make my chi-square value 12.33. I did my math ahead of time to try to make the video a little bit faster for you. If you find an error in my math, please let me know as soon as possible so I can get that information out there to everybody. Alright, so my chi-square value is 12.33. So now I need to look at the chart here. Again, my degrees of freedom is only 1. So that means my critical value is 3.84. So remember how that works. If your chi-square is less, then you accept your null hypothesis. So that would mean that any differences that we would see here are just due to random chance. If our number is higher, then we'll reject our null hypothesis, which means there's something going on here. In this case, well, 12.33 is a lot higher than 3.84. So we are going to reject our null hypothesis. Something is going on here with our variables that we would need further testing or further research to figure out what it is. Alright, let's take a look at our next problem. This one will be a little harder, but it's still a genetics problem. This one would have belonged to a dihybrid cross. Alright, in corn plants, purple kernels are dominant to yellow kernels. Smooth are dominant over wrinkled. In a dihybrid cross, where there's a 9:3 to 3:1 phenotypic ratio, or that's expected, our following data is collected. Okay, so let's see, what do we need to do here? Well, at least my sheet here has our observed values already written in, so that saves me a step there. Let's go ahead and write the totals at the end. So if I add all those numbers up, it will be 429. Alright, so for my expected values, it already tells me I expect a 9:3 to 3:1 ratio. Well, remember, all of those are out of 16. If you remember how to do a dihybrid cross, all of these are out of 16. So we expect purple smooth to be 9 out of 16, purple wrinkled 3 out of 16, yellow smooth 3 out of 16, and yellow wrinkled 1 out of 16. If I get my percentages for this, 9 out of 16 is about 56%, 3 out of 16 is 19%, and 1 out of 16 is 6%. Add all those up, that should equal 100%. Just like adding all of these up equals 16 out of 16. Okay, so now I need to find out my expected values. So 56% of 429 then will give me 240.24. 19% times 429, that will give me 81.5 for both of these. And 6% of 429, 25.74. Alright, now I've got my observed and my expected values. Again, I don't have a chart, but I don't really need one. I can write this out if I like. And alright, I'll do the first one here. I would take my observed, 223, minus expected. Remember to square that. And then divide by expected. And now I'll pause the video so that it goes a little quick. Alright, I wrote them all in quick for you. So each of these, observed minus expected, square that answer, then divide by expected. For this one you'll get 1.24. This one you'll get 0.08. Notice I'm putting a plus in between each of these. This one I'll get 0.69 and then 2.05. Add those up and you'll get your chi-square. I got my chi-square is 4.06. Again, if I did any of my math wrong, let me know. It could happen. My degrees of freedom, I have 4 categories here. 1, 2, 3, 4. Minus 1 gives me 3 degrees of freedom. 3 degrees of freedom. My critical value is 7.82. Alright, so 4.06 is less than 7.82, so it looks like I'm going to accept my null hypothesis. Looks like our Mendelian rules are working rather nicely on this experiment. That any differences from my observed to my expected are only due to random chance. There's nothing funky going on here. Alright, so that's how you would do a problem like that. Let's try something a little different here. Alright, here's an experiment often done in AP Biology. We would have done this one 4th quarter. You ever heard of roly-poly bugs? I pulled them up on my phone. They're also called pill bugs, isopods, or such. They're related to insects. They're in the arachnid phylum, or excuse me, the arthropod phylum. Alright. So often an experiment is done to see what kind of environment they prefer. So if you could imagine like a little area where they could literally choose what kind of chamber they would like to go to, and their chamber might look like this. In this case, we're going to take 12 bugs, or I shouldn't call them bugs, 12 isopods, and we're going to put them right in the middle. And then we're going to give them some areas and some time to choose where they would want to go. So the 3 chambers they have is a chamber that has no cover. So this is the control chamber. Then one chamber has a wet paper towel, and another has leaf litter. Alright, so then we start the experiment by putting them all in the middle and then giving them some time to go to where they want to go and see where they'd like to stay. So in this experiment we gave them 10 minutes. At the end of the 10 minutes we found 2 in the control area. Then we found 4 under the wet paper towel and 6 under the leaf litter. So we're wondering, is this statistically significant? Do the isopods prefer the leaf litter because 6 of them went there and such? We want to tell they 4. Well, the conclusions prefer freedom 2. Let's fill in our numbers. Remember, the null hypothesis is there's no difference between the control and the other habitats as the isopods move between their different habitats. So because of that null hypothesis, then our expected values are going to be equally divided, that we would find 4 in each of the chambers at the end of 10 minutes. However, for the observed, we had 2 in the control, 4 under the wet paper towel, and 6 under the leaf litter. Now we're going to do that math again. So I went ahead and paused the video while I put my math in here. You could use the chart if you like. Sometimes I just like to do it like this by hand. So for this one I would get 1. Don't forget to add each one. Then I would get 0 for that one and 1 here. So my chi-square is actually right at 2. Let me move that up. All right. Let's take a look. Our degrees of freedom is 2. So our critical value is 5.99. 2 is less than that, so we will accept the null hypothesis. Right? There is no difference between the control and the other habitats. So that means having 2 more of them go down in here to the leaf litter. That's really not enough for me to say isopods prefer leaf litter. That's just not enough. It's not statistically significant. All right. To speed up our video, I actually did this one ahead of time, but I'll take us through it. An AP biology student, that's you, wanted to determine if temperature had an effect on the amount of time it took for an enzyme to react to its substrate. All right, now you're going to have to start thinking back to enzymes. So the student put catalase, there's the ACE ending enzyme, an enzyme isolated from the peroxidase of beef liver cells. All right, they put catalase and exposed it to hydrogen peroxide, H2O2, while testing 2 different environmental temperatures. And our data is listed below and is collected in number of seconds that it took for the reaction to reach completion. The student expected their hypothesis that each of the reactions would take 20 seconds in any given temperature. All right, so I have that in my expected chart here. But the actual results are as follows. In the control, which is room temperature, it took 10.5 seconds. In the hot temperature, where they actually microwave the enzyme, it took 120 seconds. And finally, in the cold temperature, where they had the enzyme on ice, it took 67 seconds, or a little over. Did this student get what they expected? Let's see. Well, we have 3 categories, so our degrees of freedom is 2. Let's do our math. So I wrote that all out down here. Our observed minus expected divided by expected. Oh, don't forget to square that up there. Don't forget to add all the values together. As you can tell, what this student was thinking was way off. You probably are already thinking to yourself that you remember denaturation, right? That, well, when we put an enzyme in a microwave, that can denature a lot of it. And cold can slow it down. So I guess I was kind of expecting these types of results. Our chi-square is huge, 614.95 for our degrees of freedom. Well, we would have only had 5.99 as our critical value, so obviously with a huge number like that, we will be rejecting that student's null hypothesis that temperature does not make any difference. on the results that really something is going on here, and as I already said, it's denaturation and the environment slowing the enzyme down in the cold. This is a nice big problem, but it's just like one we actually did this year. It's the photosynthesis floating disk assay lab. All right, 2 students conducted the photosynthesis floating disk assay with spinach leaves. The students wanted to see if there was a difference between having carbon dioxide, aka baking soda, dissolved in the water, or not in the cups. This is what they tested. Their control was just having the 1 tablespoon of baking soda, and then they did all these other variations on that, from having a half tablespoon, teaspoon, half teaspoon, just a sprinkle, and then none at all. Now, I'm not really sure of what they're thinking here to get their expected results, but that's what we're going to record in the expected area, how many discs they expect to be floating after the time frame. They expected all 10 discs in the control, 5 in this one, 4, 3, 2, and 0. Well, then they actually did the experiment, and here's what they found. 10 in both of those. 9, 4, 1, and 1. All right. Now I'm going to pause the video while I do the math, and we'll see. All right, my math is done. I actually used the chart this time since I had so many categories to keep track of. And again, if I did my math wrong, please let me know. 6 categories here, so my degrees of freedom is 5. Here's the results of my math, and when I add all of those up, my chi-square is 12.08. Let's see what we've got for our critical value. 5 degrees of freedom, 11.07. Oh, looks like we're going to reject our null hypothesis. Our differences and variations are not due to random chance. There's something else going on here that we would need further research to figure out what it is. Maybe baking soda and carbon dioxide really do have a bigger impact than we think. Or maybe there's something wrong with the water, who knows? Or the amount of light, or some kind of variable is messing this up. All right, so that's an example of how you can do the chi-square test with a lot of the different labs that we've done this year. So now you'll have some problems assigned this week. Don't forget to watch the first video, which gives you the answers to last week's M&M problems, and then gives you data for this week's M&M problems. Remember, this week we're doing peanut M&Ms. Alright, so you have to watch the first video to get the data on that. And again, you can pause and replay any of these sections to help you out with this week's problems. Let me know if you have any questions. And again, let me know if you see any errors in any of the math that I did here. I left my good calculator at school, and so I'm left with my dollar calculator here at home, or I guess my cell phone too. All right, everybody have a great week.